Welcome back, environmentalists, and this is our last lecture on the natural disasters section. This is lecture 14. That means we got 6 more to go after we finish this one, so that's pretty exciting for the semester. So we'll be looking at tectonics, earthquakes, and tsunamis today, some of my topics of interest and expertise as a geologist. So we're going to introduce you to the theory of plate tectonics and continental drift and talk about the guy who really was kind of the pioneer of this field. And then we'll talk about the causes and impacts of earthquakes and identify why several of them are historically significant. And we'll talk about how a tsunami forms, how they're different from a tidal wave. And then we'll look at some historically significant tsunamic events as well as extraterrestrial plate tectonics. So, what is plate tectonics? Well, I can remember going through my grandma's stuff when she died and found maps from the early, like 1910, 1908-ish time frame, where she was a high school teacher and there were no mountains in the middle of the ocean basin. And I asked my mom about it, and she's like, well, it's because plate tectonics hadn't been discovered at that time. So what is plate tectonics? It's the study of the processes by which the lithosphere plates drift over the asthenosphere. So you might be wondering, what's the asthenosphere? It is the section of the mantle that's kind of like a mushy rock. And it is the area where we have convection happen in the Earth's mantle. So there's 3 major parts to the Earth's interior. The core, and there's an inner solid core, an outer liquid core, then there's 3 layers of mantle, and the middle layer is the asthenosphere. And the top layer, along with the crust that we have at the surface, both oceanic and continental, make up what we call the lithosphere. So there are 2 types of plates that we find in the lithosphere. There is oceanic plates, and these are very dense because they're made up of hard, metallic, basaltic, which to you in this class it really doesn't matter, but if you take physical it will. But essentially they have iron in them, so they're kind of dense, and they're very young geologically. So the plates, like if we're looking at an ocean plate, for example, down in here, this plate is dense. So if we look at these plates where you see these big mountain ranges at the bottom, right down in here, there have been times in geologic past and even currently where some of these ocean plates are smashing into continental plates. And so a very good example of some of that occurs right in this area right here. If you could see all of North America, we could show you what's happening on the west coast, and certainly this side of South America, there's some subduction happening there. So the fact that the ocean crust is very young and the oldest stuff is right along the edges of these subduction zones is a big mystery and question that was kind of proven after World War II. The average thickness of these plates is 4 miles, so that's not very thick of oceanic plates. However, think about continental plates, and they are extremely old and thick. So like the first day I have physical geology with my students face to face, I give them a little chocolate bar, Hershey's little kiss bar that's, like an inch wide and maybe half an inch thick, and I give them marshmallows. And we look at that. I know that sounds kind of hokey, but it's a really good analogy of the thickness and coloration of the 2 different crusts. So continental crust is super thick. Don't get me wrong, it's not like marshmallow soft, but in comparison to oceanic crust, the oceanic crust dives under the continental crust because it's more dense. So we can have up to literally 70 and 80 miles thick of continental crust. Continental crust is less dense. It's made out of primarily granite-based rocks, and you might go, well, that's rock solid, and it is. It's over 3 billion years old, and it's an average thickness of 20 miles thick. It's going to be your thickest under mountain ranges like the Himalayas or the Rockies or the Swiss Alps. And it's going to be its thinnest right along the edges of a continent right in here. So plates have been moving around for hundreds of millions of years. There's actually 2 supercontinents that have been documented by geologists throughout geologic past. So we'll only focus on the more recent one of the 2, which is called Pangaea. But over the past 700 million years, our plates keep arranging and rearranging, and you can see it starting at the late Precambrian. We'll go through this one time, and we'll actually saw both supercontinents. And by the end of the Mesozoic, it's pulling apart, looking like it does today. So I'm going to kind of stop it as we get to here. Well, didn't work. Go back. When you get to a point at the end of the Paleozoic, you'll have our supercontinent known as Pangaea forming, and by the end of the Cenozoic, our plates are where we know they are today. So eventually this process will stop once the inner core cools off, much like Mars did. So what's Pangaea mean? This is the actual spelling from Alfred Wegener's book, and its term means all lands in Greek. So at one time, our continents at the end of the Paleozoic era, which was back at the Permian period, were all together as a supercontinent, and there were 2 sections to that. One section is called Gondwanaland, and that's all the southern continents, and the northern continents were called Laurasia or Eurasia. So circumstantial scientific evidence exists that verifies that Pangaea came together. Like there's matching fossils on the Gondwanaland continents, which are things like South America, Africa, Australia, New Zealand, Antarctica, and even India. I know you're going, but India's in the northern hemisphere, Elaine. Well, it wasn't back then. So we have all these matching fossils. We have glacial striations, which are scratches that the rock make, or should I say glacial rocks, not. We have glacial rocks known as moraines that we can calculate. Not so circumstantial, we have geologic formations that match on different continents that have been separated by ocean basins. And then we had the geometric fit of continental shelves. So plate boundaries have been proven since the plate tectonics or continental drift theory came to be. So let's think about plate boundaries for a minute. Alfred Wegener is the father of continental drift. He couldn't come up with the plate tectonics theory. That really wasn't discovered until after World War II. And that came because we're mapping the ocean floor for figuring out where enemy subs were being held during World War II, and also where we could hide our subs from enemies. And then after World War II, the deep sea drilling program came into existence, and that's pretty much where we learned the rest of the story. So what we know is that there are plates that move apart from each other, like these right here, where you see the arrows pulling apart. That would be a divergent plate boundary. And there's several different kinds. And then there's some that move side to side, like this one right here is just scooting next to the Pacific plate is moving sideways as relative to North American plate. That's called a transform plate boundary. Then you get a convergent plate boundary, like the Nazca plate smashing into South America. You can see the little teeth right here. We have some up here where Juan de Fuca is subducting under Washington State, Oregon, creating volcanoes that we learned about in one of our previous lectures, like Mount St. Helens and all of the sister volcanoes that exist in that area. So let's kind of focus in on plate tectonics and faults. When plates collide, pull apart, or slide against one another, faults can form. And we have one in Texas that's pretty important called the Balcones. And the Balcones used to be extremely active, so we would have had earthquakes in this area. So why do faults form? Faults occur when a rock layer breaks apart and or shifts, but you have to have offset. In other words, you either move sideways, the rock slips sideways, or you move vertically up or down. And the rock or the crack in the rock must actually be offset. This creates seismic waves that travel through the lithosphere. That includes the oceanic crust, continental crust, and the top layer in the mantle. And that creates earthquakes. Faults can be active or non-active. Some are in a state of dormancy. And certain faults are more prone to slipping, which causes more damaging earthquakes. So let me give you an example. Some faults have lubricants, and you might go, oh, they'll slip better. Well, they actually don't slip as dramatically. And those lubricants are things like gypsum or talc that can be formed in areas. You're like, well, I don't understand the talc. Well, take physical and I'll explain it to you. But you can call me if you have a question on this one. But talc is actually a metamorphosed rock that's soapstone. And so that doesn't slip as well. Well, should I say it slips nicer? It's not hanging as tight. So when rocks actually are locked up like this, the more abrupt the pull apart, the more energy is being released during that earthquake. So remember the three types of boundaries are divergent, convergent, and transform. Let's look at each three. The diagram on here actually shows you a hot spot where we have a deep sea trench right here. So this is an oceanic plate and an island arc being formed right here. So this would be more along the lines of what you're seeing in number 2. Well, let's start with divergent. It occurs when two plates move away from each other. The most typical is in the ocean where two ocean plates are separating. That's called a mid-oceanic ridge, R-I-D-G-E. Important to get the spelling right of ridge versus rift, because an MOR is in the ocean where ocean crust is pulling apart, and a rift, R-I-F-T, is where two continents are pulling apart. Ultimately, a successful rift will create a brand new ocean basin. On convergent and subduction zones, these are the real exciting things that make lots of volcanoes. And you'll certainly have volcanoes on divergent plate boundaries everywhere, whether it be on land or it's in the ocean. But in a convergent and subduction situation, you're going to have some pretty impressive volcanoes because you're partially melting ocean crust and continental crust. So the two blend together and you can make some pretty interesting stuff. Now on transform plate boundaries, that's just like a pair of scissors where the plates are moving side by side. And as they do, you don't get the volcanoes, but you get lots of earthquakes because you'll get rocks that are held up and then they slip apart. So when that occurs, you'll have earthquakes like we do along the San Andreas Fault. So to define a divergent plate boundary, to be specific, a mid-oceanic ridge, an MOR, occurs when two oceanic plates pull apart because of crustal heating. There's a hot spot under there. There's, FYI, about 55 hot spots identified around the world. A rift zone occurs when two continental plates pull apart. And a great example of a rift that you might think of is the East African Rift, where the east section of Africa has a whole bunch of volcanoes and they're stretching apart. Part of that rift is more noticeable as the Red Sea. And the Red Sea is kind of where the Arabian Plate and the African Plate have been separating for millions of years, and now there's a sea there. But there's a little bitty piece of land that's a triangle that's still holding on, and once that pulls apart, we'll have a new ocean. So this is actually a divergent plate boundary in Iceland, and I'm wanting you to see that this stuff matches on one side versus the other. So I've been to Iceland. I can tell you there are places where you can reach both tips of your hands stretched out and touch both sides. One North American continental plate and the other is the Eurasian plate. But some of it's wider than others because the rift has been separating for millions of years and it's kind of at a different speed in different places of the rift zone. So when you get a convergent or subduction zone, there's two types of convergent boundaries. There's where two continents smash together. So it'd be similar to India smashing into Eurasia, and when it does, this creates the tallest elevation mountains such as Mount Everest. Big honkin' huge mountains. Subduction creates mountains and they're sizable like the Andes, but because the ocean plate sinks beneath the continental plate, the mountains are not as tall. The difference between the two is you have extreme volcanism with the subduction zone. I'm not saying you can't have volcanism with a convergent boundary where you have two continents smashing together. If you do, they'd be the worst of the worst because of the chemistry of the magma. It would be very explosive. So here's continent to continent boundaries. Look at how tall these mountains are. So basically what's happened is the Indian plate smashed into the Eurasian plate and uplifted the entire Himalaya mountain range. We have a very active subduction zone in our United States, North American area, and it's called the Cascadia Subduction Zone. And I've driven and studied this entire area on my sabbatical. And it's very fascinating. Right about here is where it's very, very close to the coastline, and you can actually go look at some places where there are markers talking about the subduction zone. So eventually this is going to split, much like we've seen tsunamis that did in Japan and Sumatra, and we're going to have a really, really bad natural disaster in that part of the country. A transform plate boundary is where they slip next to each other. So good look at this, where ocean crust and continental crust are. You could have two continental areas sliding by each other, but typically it's ocean crust and lithospheric crust, or ocean to ocean crust, that's sliding next to each other. There's one place in the world where you can actually see this above land, or above water, should I say, and it's here at the San Andreas Fault. So this is San Andreas Fault is exposed for about 800 miles total. About 600 or so miles are on land, meaning above water, sea level. And then the rest of it's in the Pacific Ocean basin. So it's just sliding where the Pacific plate's kind of going in a northeasterly or northwesterly, direction, and the North American plate's kind of moving at a southeasterly direction at about 5 centimeters a year. So do we have extraterrestrial plate tectonics? The answer is yes. We have seen it documented on other celestial bodies. Mars would probably be a really good example because it had active volcanoes, but does it have plates? The lithospheric plates are the key, so you have to determine if a planetary structure or body has lithosphere plates. One of Saturn's moons, pictured here, produces massive ice geysers, and it's really kind of cool because they spray. And then you get to see that happens from its internal heat, so kind of a fun thing to know. Let's get into earthquakes and talk about what they are and what they're not. An earthquake is caused by a sudden release of energy in the Earth's crust or the upper mantle, usually caused by the movement along fault planes. So rocks have grabbed, they released, and they release their energy. Sometimes an earthquake can be caused by volcanic activity, such as Mount St. Helens. And either way, any case, even an earthquake generated by humans and some kind of dynamite or rock crushing operation, it generates seismic waves, which can be destructive. Earthquakes typically last less than a minute. However, some of our really large ones on the Richter scale have measured up to 10 minutes in length. And it's usually because of the size and length of the fault that they travel along. Earthquakes are also referred to as the Earth's adjustments, kind of like an attitude adjustment. This picture actually came from the San Francisco 1906 quake and fire that is an important element. On earthquakes, there will be no less than one earthquake somewhere on our planet today. There's earthquakes happening every day, every hour. Most of them are very tiny. Not all earthquakes are strong enough to be felt on the surface, and that's why we don't know about them. But most earthquakes are so soft that only scientific instruments can detect them. So the Richter scale works on the amount of energy released, and then there's a separate scale that measures damage. Most earthquakes don't occur in highly populated areas, and that's another reason we don't hear about them. Despite the fact that there are earthquakes happening every day, scientists still have no way to accurately predict the moment and timing or intensity of an earthquake, but we can certainly guess and plan for areas that we know should have high probability of creating bad earthquakes. Since earthquakes occur so frequently, the only real statistic that we look at is an estimate of how bad it will be and when it happens. So you can see some offset of crust right here. That's not a good thing to have experience-wise. Hopefully, the earthquake was not too large to cause a lot of damage to human life and structures. So what are the causes of an earthquake? Typically, a tectonic plate moves and collides. That's one reason. Stress concentration along a weak spot within a rock mass, commonly along a fault line, can create that where the fault finally just slips. Activation of rift valleys near the middle of existing continents where magma is rising to the surface and heating the crust as hotspots. We also see migration of magma to the surface in a volcano that can actually stretch and create earthquakes to occur. And believe it or not, meteorite or meteors that strike the earth can actually create an earthquake, and those are very, very rare. So there are different types of seismic waves, and basically seismic waves are used by geologists to determine the type of geologic stress applied either inside the earth or on top of the earth. So when the stress on plate becomes too great, the rock mass that makes up the plate breaks under the pressure of the stress causing forces and sends out seismic waves throughout the body of the earth from the breakage site. Surface waves typically inflict high levels of damage in nearby places from the epicenter as soil and rock shifts violently to counter the underground movements. So there's really two types of seismic waves. There's body waves and surface waves. And it's the body waves that cause most of the damage at the surface. So let's look at those body and surface waves. A stress wave, that's a body wave that transmits through the interior of a three-dimensional object. In this case, that object is a tectonic plate for the Earth. Stress waves can travel through solid objects and leave the object intact. That's kind of interesting. Example, the sound energy you generate when knocking on the front door. Okay, so it left the energy went to that door, but it didn't destroy it. So that's what happens with body waves, and they're called P and S waves, P for primary, S for secondary waves. On surface waves, the stress is a wave that's transmitted along the surface of a three-dimensional object, and in this case, that object is a tectonic plate, and the waves occur along the outside of influenced object. So that's right at the crust. Example, a crater caused by a meteor strike. These two waves are called R for Rayleigh waves and L for Love waves, named after the people who first described them. So when we think about earthquakes, some terminology is important for you to know. The focus of an earthquake is the actual site inside the earth. Let's just say that this was 20 kilometers down and this is where the slippage occurred. That would be the focus of the earthquake. The epicenter is going to be directly above the focus at the surface where humans would be or where the land is. And people often think that that's where the earthquake occurred. It's really inside the earth. So if you're thinking, well, could there ever be an epicenter and a focus in the exact same place? I'm never going to say never, but it would be extremely rare because usually most faults are kilometers deep. So you're looking at the potential for at least tens of feet deep that an earthquake could occur, but sometimes they can get beyond 300 and 400 miles beneath the surface. Now, what's ground motion? The combination of all the stress waves, P waves, S waves, R waves, L waves. The magnitude of an earthquake is determined by the Richter scale, and the Richter scale ranges from 1 and is open-ended. It's also a logarithmic scale, so that means that each time you go up a point, it's 10 times more, it's 10 times worse. That's actually not true when you start reaching right around 8, upper level of 7, 8, 9s, and 10s, because it's about 30 times worse each time you go up here. Keep in mind that this is, these are hazard names, but each of these has a name. So it can go well beyond a 10. We've just not measured a 10 on the Richter since it's been invented. And it measures magnitude, which is the amount of energy released, not the amount of damage that's associated with the earthquake. Naturally, you could associate with the higher the number of Richter scale reading, typically the higher the damage would be, considering if you're in a populated area. And then you have to consider how the structures are made and so forth. There is a scale that measures earthquake damage, and that's going to be by the modified Mercalli intensity scale, known as the MMI scale. And this goes from Roman numerals from 1 up to Roman numeral 12, XII, and measures the damage of an earthquake at a certain location. This is typically assessed for two reasons. One is for planning for municipalities, for risk factors like risk management, for landslides, mudslides, so forth. And then the second reason is for insurance claims, because if you tell your insurance agent that you lost everything in an earthquake and it had an MMI rating of like a 2, they'd go, seriously? you're going to have to pay for us to come out and look at that one. We don't believe it. But if you were maybe at a 10 or 11, they'd go, yeah, we'll be taking, you can send us pictures of what's left and we'll write you your check kind of thing. This is determined from an aerial evaluation done by the United States Geological Survey, USGS, after an earthquake event. It usually takes a little time to generate these maps, but giant earthquakes, it's very important because certain areas may receive more damage than others based on fault lines, the type of rock material that's there, and how the structures are built. So when we're determining the focus, we have to know two parts to it. We have to know where P waves and S waves are and how fast they travel. So the focus is determined by comparing the arrival time of the earthquake's initial primary wave, P wave, versus its secondary wave, S waves. So P is always first to arrive on the scene. That's why it's called primary, and it travels through solids, liquids, and gases. So it can travel through anything. However, S waves are kind of selective and picky. They only travel through solids. So they also travel at about half the speed of a P wave. So if we know when a P wave first arrives at a seismic station and then a little few seconds later the S wave arrives, if we can do that, then we can start to know about how far it was from the epicenter. But we can't do it with one seismic station alone. Can't even do it with two. It must be done with a triangulation approach of 3 or more seismic stations. So a couple of more earthquake terminologies. A fault, that's a fracture or a discontinuity in the volume of rock where there has been a significant displacement along fractures associated with earth movement. So faults are typically rocks that have cracks in them, known as joints, and then that joint moves and it has either sideways or vertical offset. A fault line is a large clean fracture in earthen crust. A fault zone is a series of multiple or smaller fractures in the Earth's crust. And a blind fault, which was very important to the Haiti earthquake that you witnessed depending on how old you are, it happened a while back, but nevertheless, a blind fault was there. And this is a type of fault that typically is not seen in the crust of the Earth or maybe covered up with other geologic layers, and we haven't mapped it out, so we don't know it's there. Earthquakes cause multiple problems. First one is ground failure. You're like, well, duh, that's a no-brainer, right? Because it shakes buildings and causes landslides to form and causes displacement. It can also cause tsunamis, and tsunamis are when the seafloor suddenly shifts either up or down because of vertical offset during an earthquake. That can create waves, seismic waves, and it moves the entire profile of that water. Volcanic eruptions can also happen along with earthquakes. While this is rare, sometimes they can be triggered by a massive earthquake that shifts their plumbing and allows for a magmatic event to occur. So as we leave earthquakes before we move into tsunamis, let's get a couple of science surveys before we move on. Without tectonics, the Earth would be cooling and dying just like poor little old Mars because there would be no internal heating. That's our fate one day, but good news, that's going to be about 2 to 3 billion years down the line. You don't have anything to worry about right now. Earthquakes are responsible for most of the Earth's topography, and especially some of our really dramatic landscapes that we have. I can think about the coastline of Maui, for example, very dramatic straight up and down cliffs. Well, that happened from faults where big sections of Maui just slid right off. So, and it matches to some of the other surrounding islands like Lanai and Molokai. A fault is considered active if it has produced activity and mood within the last 35,000 years. I think I missed a point there. Earthquakes, when combined with tsunamis, represent the deadliest disaster that we will study, and they are extremely devastating. Moving to this column over here, most faults that have not produced a recent earthquake are discovered by remote sensing, which is use of satellites. Some fault activity is determined by fault trenching, where geologists dig a trench along a fault line and try to compare the soil layers to see if the horizons have been offset. Fault trenching helps determine where probable activity for seismic events could occur. And when the ground is left informed by an earthquake, the changing formation may be a permanent or temporary structure. So where is an earthquake probability? Our best places to have them are where ancient fault zones are. or where we have current mountain building occurring. So, or any active plate boundary. For example, we have very passive action over here, but used to be like the hot area. Everything went on there back in Pangaea time frame. You're wondering about some of these areas, why they're so dark. Well, most of these have to do with ancient fault lines, okay? Then you come over here with all the yellow dots, that's along the San Andreas, but right up here, from here all the way up to here, that's a different situation from the San Andreas, because the San Andreas comes out like this, goes out into the ocean right here, and it connects to the Juan de Fuca plate. So all this is caused by the Juan de Fuca subduction zone. When you look at these areas, those are all from the Rocky Mountains, so fault lines. So when you look at the active fault lines around the globe, you might want, or North America, specifically United States, you're going to say, what's up with this thing right here? And that's the New Madrid fault zone. So that's an active fault zone that's been active for a very long time, and it's dangerous because it's in the interior of a continent. Because then this material is very dense, and so the earthquake waves can travel further. So this area right here, no brainer. This is the subduction zone. Then you get, of course, the San Andreas fault right here. And all of these areas would be areas that represent ancient fault zones that are still active. Then you look at Alaska, it's made up of nothing but active fault zones because it has been kind of smashed into multiple times to create the state as we know it as Alaska. So, lesser known fault lines. There are hundreds of faults in the U.S., really thousands. The New Madrid Seismic Zone, which is what I was talking about earlier. Let me revisit the prior slide. That's this area right here, right there. So the New Madrid Seismic Zone is the most active intercontinental fault that we have currently. And it follows the Mississippi River between roughly Memphis, Tennessee to Alton, Illinois. The Brevard is the fault along the Appalachian Trail. The Helena Banks is found in the eastern coast of South Carolina, and the Ramapo Fault travels 70 miles central of Pennsylvania to northwest of New York City. And the last activity from this fault was a 5.2 on the Richter scale under Brooklyn in 1884. This one, however, has created some pretty impressive earthquakes and kind of an interesting story to look into over a 3-month period. The largest earthquakes in the United States typically occur along subduction zones. So I'm going to tell you straight up on all of these: Alaska, Cascadia, Alaska, 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 Alaska. These are all subduction zones. And if you had to put your money, if I were putting my money on where the next huge earthquake would be, I would pick one of 3 places. Either the west coast of South America, Alaska would be my first choice, and then Japan would be my 3rd choice. My 4th choice would be Indonesia. So it's no surprise to me when we have big tectonic events there in those locations because they're all subduction zones. So we're going to look at a really bad earthquake that struck the United States that kind of changed the whole world's knowledge of earthquakes, and that was the great San Francisco earthquake and fire of 1906. And then we'll look at the New Madrid earthquakes of 1811 and 1812. There are many others, but these are believed to have killed the highest number of people, and we want to take a look at them. So let's look at the Great San Francisco earthquake and fire of 1906. I'll tell you why it's called the Great. 8.0s to 8.9s are referred to as great on the Richter scale, and anything above an 8.9, which is 9.0 and higher, is called a rare great. So that's where the name great comes from. It killed about 3,000 people. The true number will never be known, and it was between the earthquake and the fire, with most of the deaths being related to fire. Remains of the deadliest earthquake in nation's history. Unfortunate. Hopefully we won't have another one that kills that many people. And it was caused by movement, sudden movement along the San Andreas. And when it moved very quickly. Some people have a false sense of these things happen slowly. Just as an FYI, I'll go back for a second. This movement happens very rapidly when you're looking at a fault zone that releases like this one. And when it did, it was over about a 30-second period, and it moved 21 feet at its greatest offset on a lateral, meaning a transform plate boundary. The New Madrid earthquake of 1811 and 1812 was not just an a quake, it was multiple earthquakes. A series of large earthquakes measuring over 7.0 on the Richter scale occurred between December of 1811 and February of 1812. It caused over 2,000 aftershocks, and over the following 5 months, where the ground was trying to resettle and find its place. And it occurred along the New Madrid Fault, roughly between Memphis, Tennessee, and St. Louis, Missouri. And New Madrid is the most active fault in North America east of the Rocky Mountains, and this represents an ancient plate collision that we had, which was the edge of the continent at that time. The New Madrid Fault line experiences an earthquake every other day, and we're like, well, how come I didn't know about that? Because they're usually pretty small. If a similar earthquake were to occur today, it would impact over 15 million Americans, as it did, similar in size anyway, to the 1811, 1812 earthquakes, because there were 3 really large ones that occurred at that time, and it would impact people in 7 different states. A large earthquake could occur at any time along this zone, and it's not a matter of if, it's a matter of when it will happen. So the deadliest earthquakes in world history, when you start to look at this, you can look at the magnitude, and some of them have a question mark because we just don't know. We didn't have Richter back then. Like, we really don't have Richter for 1556 either. It's a guess. So these really old events are guesses based on the amount of damage and literature that's available on them. But you have a pattern. Most of them are along major fault zones, either caused by 2 continental plates colliding next to each other, or you have a subduction zone. Haiti is in a subduction zone. These areas are along a subduction zone. This area, you look all the way down the chart, I totally see a pattern going on right here where they're all in those types of areas. So there's some that have happened in modern time that I think are worthy to note, and they're going to be in our tsunami event that we're fixing to talk about.
The plates are interlocked. That's why, when they shift, the jerky movement along the edges that separate them causes what we call earthquakes. Most of the earthquakes recorded in the world aren't very strong, but sometimes a particularly great one causes destruction and death. Earthquakes also occur at the sea bottom. When that happens, they can sometimes displace the water column and originate waves. These waves are best known by their Japanese name, Tsunami, which simply means harbor wave. Regular sea waves, caused by the wind, are very different from tsunami waves. Let's find out why. Wind blowing over the sea can only move the upper layer of water, forming waves, but not affecting movements deeper down. The water particles near the surface move with a circular motion, which helps to propagate the wave along. Deep down, the water particles don't move. The strength with which these waves reach the coastline depends exclusively on the movement in the first few meters of water. A tsunami, on the other hand, can be generated at the bottom of the sea. In case of a strong earthquake, the sea floor abruptly deforms and vertically displaces the overlying water. The entire water column is disturbed by the uplift or subsidence of the sea floor. This sudden movement releases a great impulse of energy, which is transferred to the whole column of water between the surface and the sea floor. In this case, the water deep down moves as well, as deep as 1,000, 2,000, 3,000 meters. Apart from submarine earthquakes, tsunami waves can also be generated by underwater landslides, or when rocks or sediments slide into the sea, by volcanic eruptions, or more rarely, when a meteorite falls into the sea. Alarm systems currently in use in the Pacific and Indian Oceans give advance warning when a tsunami is generated. These systems rely on sensors placed at the sea bottom, which measure variations in the water above and transmit an alarm via floating buoys and satellite link-ups with observation stations on the coast. Once generated, tsunami waves in the open sea travel very, very fast, up to 800 kilometers per hour. They can cover thousands of kilometers and approach coast far from their point of origin with great energy. In the open sea, The waves are rarely over a meter high and are very long, so they're imperceptible. A ship in open sea, for instance, wouldn't notice anything out of the ordinary. The speed of a tsunami wave depends on the depth of the water the wave is traveling through. Approaching the shore, the tsunami's speed diminishes, although it's still much, much faster than an ordinary wave. Also, wave amplitudes will increase dramatically. This is due to the fact that the tsunami's energy flux, which is dependent on both its wave speed and wave height, remains nearly constant. Consequently, as the tsunami's speed diminishes as it travels into shallower water, its height grows. This huge and fast-moving mass of water shifts an entire column of water from the sea floor to the surface. Approaching the coast with a destructive force far superior to any wind-generated wave, it can advance hundreds of meters inland. That's why, even if it isn't very high, a tsunami wave can still cause serious damage along a coastline. When the trough of the wave first reaches the coast, the tsunami appears to make the sea withdraw, often quite consistently, leaving harbors and beaches dry. This can last for several minutes, and is a sign to get as far away from the shore as quickly as possible. The crest of the wave will arrive at any minute. It may look like a sudden high tide that keeps getting higher, or a wall of water moving faster than any normal wave. It carries with it the energy of the earthquake, not that of the wind. This is exactly what happened along the coast of Thailand on the morning of December 26, 2004. A tsunami generated by the strongest earthquake of the past 40 years off the island of Sumatra spread death and destruction along the coasts of the Indian Ocean. Images filmed by people who were there help us better understand the devastating effects produced by the huge amounts of energy of the tsunami wave. catastrophic events of these proportions are extremely rare. In the past, the most destructive tsunamis hit the coasts of the Pacific and Indian Oceans, but even the coasts of the Atlantic Ocean and the Mediterranean Sea, to a lesser degree, are at risk and have experienced sometimes destructive tsunamis during the course of history.
The video gave you a really good overview of how tsunamis work, but it's almost incomprehensible that the entire ocean profile of water will move when a tsunami occurs. It's not like a wave generated or wind generated wave where the just top molecules of water are just recycled over and over. The entire profile is moved from the bottom of the ocean floor. And they did a good job of also showing you as it approached the continental shelf and the shelf got shallower that it slowed it down like a speed bump, which causes the front end to slow down and the back end still moving at jetliner speeds. So what is a tsunami? It's an unusually large sea wave produced by a seaquake or earthquake, and it's caused by undersea water displacement. No matter how you cut it, the ocean floor has to be displaced. The water has to be displaced down there, whether it's a landslide, a meteor strike, whether it's more commonly by a catastrophic earthquake. And tsunamis can be caused by earthquakes, seaquakes, volcanoes, landslides, and meteor strikes. They move across the entire profile at the bottom of the ocean floor, meaning the seafloor, to the ocean surface. So it's one big moving wall of water. It's a Japanese word that means quote unquote harbor wave, and it's usually more than just one wave, and it's hard to predict which one of the waves would be the most damaging. So they come in series, and it's all a matter of how those seismic waves that we talked about, PS, LNR waves earlier, are moved through that water profile. In deep waters, a tsunami may only be 1 foot high on the surface, but as you get closer to the continental shelf, that's going to change. And they travel at up to 500 miles per hour, sometimes even greater. Jetliner speeds is typically the term used for their speed travel. They're going to lose speed as they hit the speed bump as the continental shelf becomes slower, which causes this part to slow down, and the weight and movement of all of these waves are still pressing up against it, which causes it to grow vertically and laterally. So they don't lose much of their power or their speed until they hit that continental shelf. While still far out at seas, many tsunamis are only detected using scientific sensors, and those are called DARTs, Deep Ocean and Assessment and Reporting of Tsunamis. Tsunamis in a miniature. You could create a tsunami right here in a bathtub. So this is the DART system that I was just referring to a minute ago. Scientists can accurately estimate the time when a tsunami will arrive, but these DART buoys have been put in place because they're connected to the ocean floor. There's a seismometer there. There's sensors to explain how fast the water will move, meaning the speed of the wave. And if we already have topography of the ocean floor determined, we can put all that data together and put it in computerized models to help predict when the arrival of these things will occur at the next coastline. So DART buoys, known as Deep Ocean Assessment and Reporting of Tsunamis, test question, measure the vertical uplift of the ocean floor and the velocity of the tsunami waves. Where are these things located? They're located and active in the Pacific, Atlantic, and even in the Indian Ocean basins. So science surveys, 40% of all Japanese coasts have some form of seawall present having to do with issues related to tsunamis. Typically, the ocean recedes abnormally away from the shoreline for a few minutes or less before a tsunami actually hits. Don't go check that out. Run for high ground if you ever see that. In the old days, this was one of the only telltale signs that a tsunami was approaching. Tsunami is not the same thing as a tidal wave, and I would hope that none of you will ever call it that. A tidal wave actually occurs, there's such a thing, and it's caused by the moon's gravity. So most tidal waves are not the same size as tsunamis. We'd have to have the moon right on us to create that kind of massive swelling of water. So what you refer to as a tidal wave as a child is really a tsunami. And understand that tsunamis are created by big displacement of ocean water at the bottom of the ocean floor, like an undersea earthquake, volcanoes, and rarely a meteor strike. Hawaii is the U.S. state with the greatest risk of tsunamis, experiencing on average one per year and destructive event once every 7 years. Historically infamous tsunamis, it's debatable as to which tsunami is the worst since there have been so many catastrophic events. And people say, oh, they're really rare. They're not. It's just documented in human reference that they are. But there's two that we can talk about that have happened in a recent ones that are still discussed in public forums and we're still learning from, quite frankly. There's the Sumatran tsunami of 2004. It happened the day after Christmas on December 26th. And then there's the Japanese tsunami that happened in March of 2011. So the Sumatran tsunami occurred along this plate line, which is actually called the Burma plate. It's a small oceanic plate subducting under this plate over here. And this was caused by springboard subduction zone where the continental crust was being folded as the ocean crust went in, and it just went bloop like this and lifted the water. And it happened along a 600-mile fault line right in here. So that's this fault line right along this section right here. And so as it did, it was like a domino effect. And it shook for up to 10 minutes depending on where you were. And this thing was huge. It was a 9.15 on the Richter scale. So it's not even Richter. There's another scale called moment magnitude for large earthquakes like this one. So the seafloor was only lifted several meters and moved up to 10 meters. So let's do several meters is like 6 feet. But it offset by about 10 meters, which is 30 feet. And some places you'll read it was offset by 50 feet. So regardless, it's eroded flat within a few months due to ocean currents at the bottom of the ocean. It was estimated to have killed over 227,000 people, struck 11 countries from those in Africa to Southeastern Asia. Africa had the most minimal loss of life, and you can go, oh, it was the furthest away. It really didn't matter. The tsunami was traveling at the same speed. It had to do with warnings that helped save their lives. So it traveled over 3,000 miles in less than half a day and originated from a 9.1, it's really 9.15 if you want to be technical about it, magnitude earthquake, and released the energy of 23,000 Hiroshima-type atomic bombs. The Japanese tsunami of 2011, I'll never forget because I was on my pre-honeymoon, mainly because of timing for classes, because we got married in March, and we were on the cruise boat when this happened, and we got to see it in real time, because we had gone to the midnight buffet, and so we were walking back to our room, or our cabin, when we saw it all unfold. So what happened to the Japanese tsunami? It was created by a subduction zone, just like the 2004 Sumatran tsunami, considered to be some of the worst concurrent human natural disasters of modern time. And you know some of this story, you would have to, because of all the disasters that happened. It's referred to as the Great East Japan Earthquake, the 311 earthquake, because it happened on March the 11th. Tohoku earthquake. Let's watch a video over this event.
The following animation shows a Japanese tsunami propagating throughout the Pacific Ocean. As a tsunami radiates from Japan, it encounters complex topography and bathymetry in form of ridges and volcanoes that create this complex wave pattern of scattering and reflected waves. By the 8-hour mark, the tsunami had encountered the Hawaiian Islands' populated areas. After 9.5 hours, it was hitting the west coast of the United States. Notice how complex this wave pattern is becoming as it encounters more topography and more bathymetry, and now you're seeing reflected and refracted waves throughout the entire Pacific. At the 16-hour mark, the tsunami now has propagated throughout the Pacific and is entering the Indian Ocean and enveloping the New Zealand islands. At 22-hour mark, the tsunami had propagated throughout the entire Pacific Ocean. One way to simplify the interpretation of this complex wave field is to compute the tsunami energy pattern shown on this map. The red colors indicate where the maximum force is directed.
So Fukushima is the famous disaster that happened as a consequence of the tsunami, and this was a large fishing community, but also home to a large industrial centers for manufacturing, importing, and exporting, and also the site of a nuclear energy plant. It's home to a seawall and TEPCO's nuclear power plant along the coast, which happened to be ground zero for the worst damage of the tsunami because of the nuclear power plant. What a surprise, right? So, when we look at this, the tsunami is estimated to have caused $122 billion in damages in 2011 dollars. And it's estimated that 20,000 people drowned, and one of Japanese ghost ship was found off the coast of British Columbia, Canada in March 2012. So this is that ship right there. So extraterrestrial earthquakes and tsunamis, can they happen? Could they happen? Earth is one of the best planets to study tectonics and tsunamis, but tectonics occur in other places throughout our solar system. They still call them earthquakes because the Earth is a word that means raw dirt. The E is not capitalized in this particular case. Titan, Saturn's moon, definitely has earthquakes. When it comes to tsunamis on extraterrestrial areas, we might surely have them in places that have some form of liquid. Europa would be an example. It's tectonically active, covered in water, and likely the home to highly pressurized ocean. So it has a fair chance that it experiences some form of a tsunami that is simulated or stimulated by tectonic activity. Tectonics are thought to be what caused the visible cracks in the ice's surface of Jupiter's moon known as Europa. So as we conclude for the day, it'd be very misunfortunate that you would be riding on a wave of a tsunami because I don't think you'd like what you encountered when you get to shore. As we conclude our series on natural disasters, take a moment to recognize that everywhere on the planet there is a risk, a natural disaster, a storm, a hurricane, cyclone, some kind of a event, whether it be a tsunami, a volcano, an earthquake. So it's not like you can escape it. You have to make a decision where you're going to live based on the factors of where your job, your family wants to be, and then look at the risk management assessment of the types of natural disasters that are located there. I hope to see you at the next lecture. Bye.